I would like to introduce Professor Santosh Nagarakat. He is an associate professor and undergraduate program director of computer science at Rutgers. He obtained his PhD from the University of Pennsylvania and in 2012. His research interests are in hardware-software interfaces and spanning programming languages, compilers, software engineering, and computer architecture. His papers have been selected as IEEE Micro Top Picks Papers of Computer Architecture Conferences in 2010 and 2013. He received the NSF Career Award in 2015, ACM SIGPlan PLDI 2015 Distinguished Paper Award, and ACM SIGSOFT ICSE 2016 Distinguished Paper Award for his research on LLVM compiler verification. His papers have been selected as the 2016 SIGPlan Research Highlights Paper and 2018 Communication of the ACM Research Highlights Paper. His papers on correctly rounded elementary functions have been recognized with the ACM SIGPlan PLDI 2021 Distinguished Paper Award and the ACM SIGPlan POPL 2022 Distinguished Paper Award. Not bad for a guy who's only been a professor for less than 10 years. Really impressive. Santosh, would you like to start just slightly early? I think we're ready to go.
Okay, so can you guys hear me? Okay, so awesome. Thanks, John, for the generous introduction. And I thank the organizers for inviting me to give this talk. So today I'm going to talk about our project, which I call RLIBM, to generate correctly rounded libraries. So my goal of from this talk is to show you some evidence that it's feasible to design both fast and correct math libraries. Okay, so you don't wake up and start designing math libraries, right? How did I? Let me tell you a story about how I started designing math libraries. Okay, so for a long time, I have been working on proving the correctness of compiler optimizations. And we have had some luck where like our tools for compiler optimizations have been adopted by industry. So effectively, we take compiler optimizations, encode it into first order logic, and use automated theorem provers and prove its correctness. And so we found a lot of corner cases in compilers. In this process, we discovered that even when compilers don't want to do anything with floating point, they get floating point optimizations wrong. So a simple bug that has been lurking around in a mainstream compiler for 10 years was flipping the sign of 0. William Kahn has a fantastic paper on how it causes issues with branch cuts. So we got excited about it. We reported the bug. It was fixed immediately. And then compilers have this amazing mode called as the fast math, where it treats any identity with real numbers as an identity that holds with floating point and optimizes the program. For example, associativity. Associativity is not true with floating point, but like it treats associativity as holds and parallelizes the code. And you may think like, how does it matter, right? So it turned out like I had a fantastic student who trained a neural network, again, a custom neural network. And all he did was he trained it with fast math and trained without fast math. The accuracy without fast math was like around 89%. And then we ran, all he did was change the rounding mode, ran fast math, the accuracy dropped to 25%. And then we wanted to debug what the hell is happening, right? So how do we go about debugging? And there are no tools available. So then we decided, okay, let's build a shadow execution framework where we take the original floating point program. This is the training, the model, the training infrastructure for the neural network. And I ran it with a high precision version of the same program. So we would simulate like a high precision version with the MPFR library, and we would compare the results lockstep at every step. We wanted to figure out where the error is occurring, and then how this error is getting propagated. To our surprise, we found math libraries where the instances where the two programs were divergent. So what are math libraries? These are elementary transcendental functions, e power x, ln of x. So you may say, okay, so it's 1 alpha error or 2 alpha error, who cares, right? So in our case, like we took the same program, we started debugging on an Intel machine, and then on a GPU to accelerate it, the results were completely diverging. This was the issue that John was just mentioning in his introductory note, right? So it was like you couldn't reproduce the errors. It was like a debugging nightmare. And then on, what would happen is this small rounding error would get amplified with catastrophic cancellation. And then you would have branch flips. Your program would take different branches compared to an Oracle execution. You would have slow convergence. And the worst of all, you would get nans and infinities in your program. And then once you get nans, everything gets poisoned and you have total weird results at that. So this is where my foray into elementary functions started. So I wanted to understand, okay, how are people designing elementary functions? And why are they not producing correctly rounded results? So I want to emphasize here, IEEE 754 standard mandates correct rounding for primitive operations, addition, subtraction, multiplication, and division. It does not mandate, it recommends correct rounding for elementary functions. As a result, no one implements correctly rounded elementary functions. Okay, so now I've been talking about correct rounding. What is correct rounding? So let's look at a number line, a real number line. So there are infinitely many points, right? So only finitely many of them are representable with any finite precision representation. Let's say floating. So here V1, V2, V3 are values representable with floating point. Okay. So now you compute a transcendental function with the best state-of-the-art algorithm, and it produces a real value. And in most cases, it won't be exactly representable in your floating point representation. And then you need to round it. So generally, there is a rounding mode associated with most representation. So the most commonly used rounding mode is round to nearest, I goes to equal, right? So now when you round this real value according to the rounding mode, you could get V2, which is the value that is representable in your floating point representation. This V2 is the correctly rounded result. Let me emphasize, you compute the transcendental function with real arithmetic and you get a real value. And finally, you round it according to the rounding mode and you get a value in the floating point. This is the correctly rounded result. Okay. So now, how do people approximate this correctly rounded result? So as we are talking about real arithmetic, people use classical results from approximation theory. So Weierstrass approximation theorem and Chebyshev's approximation theorem. They all say how to approximate the real value of a continuous function. Okay, so everyone approximates the real value of f of x. And now, as you can see in the figure, you can only do this approximation very well if it is over a small domain. So if your domain is the entire floating point domain, the dynamic range, that is minus 2 power 149 to 2 to the power of 128. So no approximation is going to work. So you can do approximation effectively over a small domain. So you need to reduce the domain of the function. And this is called as range reduction. So what do? You have an input over the entire domain, you reduce it to a small domain. In the case of land function, you would want to reduce it to 1 to 2, let's say. So you reduce it and then you would invoke results from approximation theory. One classical way to approximate over a small domain is a mini-max approximation. What are you trying to do? You're trying to create a polynomial that minimizes the maximum error across all points. Okay, it's classical results, they're fantastic results from it. And then you would generate the result, the polynomial, you do the polynomial evaluation over the minimax polynomial that you obtain, and then you would compensate it to produce the result for the original input. So effectively, there are 3 steps, right? First, you have range reduction, which reduces an original input to a smaller domain. And then you have polynomial approximation, a minimax polynomial that is generated. You evaluate the minimax polynomial over the reduced input. It produces the output for the reduced input. And then you compensate the result to produce the result for the final, for the original input. So this range reduction, polynomial evaluation, and output compensation typically happens with some finite precision representation, which is you want it to be supported by hardware. So let's say a double or something that is natively supported in hardware. Okay, so now why do these approaches produce wrong results? Okay, so let's consider a result of an elementary function which is very close to the rounding boundary. Here, V1 and V2 are 2 adjacent points with respect to this blue dot, which is the real value produced by an elementary function. And this blue, the real value of the elementary function, is very close to the rounding boundary, which is the midpoint of V1 and V2. So now the amount of freedom that the minimax polynomial has is shown in the gray bar on the slide. Since it's very close to the rounding boundary, this is the maximum freedom that you have. Now you need to generate a minimax polynomial with extremely high amount of accuracy. So alternatively, what typically happens is the minimum error generated by a minimax polynomial is more than the amount of error threshold that this input can tolerate, and this results in wrong results. Further, you're implementing range reduction, output compensation, and polynomial evaluation in some finite precision representation. So it's going to have numerical error. So it may cause the eventual result to be slightly beyond the amount of toleration that you have for this input. As a result, you get wrong rounding. Okay. So if you're designing a math library, what do you want to typically produce? You want to produce a correctly rounded result. So one of the key insights of the RLIBM project was we want to produce correctly rounded result. Why are we worried about the real value of the transcendental function? Okay. So John was alluding to table maker's dilemma, right? There are two main challenges in producing correctly rounded results. One, having an oracle that tells you what should be the correctly rounded result. And this is what table makers, like, you don't know how much precision you need to evaluate like your algorithm to produce the correct result, right? Especially when you have a value that is very close to the rounding bound. And then if someone gives you an oracle, how do you actually generate an approximation that is fast and still produces the correctly rounded result? So one of the insights that we had from John's paper, Minefield Method, was, okay, so your goal is to produce correctly rounded results, approximate the correctly rounded result directly. So this requires us to have an oracle. In our case, like, we use MPFR libraries, which is simulated with 22,000 bits of precision as our oracle. We use those algorithms, produce the oracle. Once we have the oracle, our goal at hand is to produce an elementary functional implementation that is extremely fast and produces the correctly rounded result. Okay, this is the first insight. Like, if you want to take away three things from the top, the first thing I want you to take away is, if your goal is to produce correctly rounded results, directly approximate the correctly rounded result. Don't use real value as a proxy to generate the correctly rounded result. Okay, so now once you decide to approximate the correctly rounded result, there is an interval of real values around the correctly rounded result. You produce any real value around this interval, it rounds to the correctly rounded result. This is the maximum amount of freedom that you have to produce your polynomial has to produce the correctly rounded result for this interval. And what we show in our papers and in the project is this freedom is much larger than whatever you typically get with a minimax polynomial. Okay, so if you approximate the correctly rounded result, you have a freedom, which is like the rounding boundary that produces this exact result, right? So that is the total maximum amount of freedom. So one thing you need to do is you still need to take into account, when you compute this boundary, any error, any numerical error that may occur with range reduction, output compensation, and polynomial evaluation. So adjust the boundary. So the first thing that we do is we approximate the correctly rounded result. Once you approximate the correctly rounded result, there is an interval of real values around this correctly rounded result. You produce any value in this interval, it produces the result that you want. So now what is our algorithm for it? You have an elementary function, you have a representation of interest and a rounding mode that you are targeting. For every input, use an oracle to produce the correctly rounded result. Okay. So all we are doing is like we are using an oracle. So we are not solving a table maker's dilemma. We are just punting the table maker's dilemma onto the side. Like, let's someone solve the hard problem. So what we are doing is like we want people to use correctly rounded result. So use an oracle and identify the correctly rounded result. But why can't you just use MPFR correctly rounded libraries, right? Because they're very slow. No one wants to wait like 2 hours for your neural network to just give a single answer, right? So you want fast libraries. So this is the goal of the RLIBM project. Now you have a representation, you have a function, you have a rounding mode. I use an oracle, generate the correctly rounded result for all inputs. And then what do? Identify the rounding interval corresponding to the correctly rounded result for each input. Okay. This rounding interval is the freedom that you have for the polynomial. So what should the polynomial do? When you evaluate the polynomial on a particular input x1, so it has to, if the interval is L and H, like the lower bound is L and higher upper bound is H, the result of the polynomial has to be such that it's greater than L and less than H. So now how many constraints do you have? You have as many points you have on the in your representation, right? So it's a system of linear inequalities. Okay. So now what are we trying to do? We are trying to solve for a polynomial. So what is a polynomial? It's C0 plus C1x plus C2x squared. Then what are x's? X's are input points. So what we are looking for is to find the coefficient of coefficient C1, C0, C1, C2, the C on, CD. In the case when the D is the degree of the polynomial. So this is a system of linear equations, like, and there are like amazing LP solvers out there, just use them. So again, there are like, you have billion constraints, how do you solve them? No LP solver can handle them. So, but the key observation is, this is a linear program of small dimensions. You have lots of constraints, but like very few variables. We have a clever algorithm. We can talk about it after the talk if you're interested. So what have we done? You approximate the correctly rounded result, and then you have an interval of values around the correctly rounded result that imposes a linear constraints on the output of the polynomial. Now we have a system of linear inequalities corresponding to every point in your representation. Solve this, you get the coefficient. And there you go. So since you have the largest amount of freedom compared to any approximation that you could do, the resulting polynomials are very fast. Okay. So if all you had was one representation, one rounding mode, the world would have been so good, right? Like now you have results, you have like functions in math library, let's produce all of them. But unfortunately, like floating point performance, or like any approximation, like posit or float 16, like any approximate, people are designing new representations to approximate real numbers, and their performance is amazingly important. So one of the questions is, how do we generate? Like, we don't want to be generating like new math library for every representation and every rounding mode, right? So from a library designer viewpoint, like you are the maintainer of libc, you don't want like 20 different functions for every, because like once the code is there, like it's always there, like identifying what it does 20 years hence is going to be very difficult. So and people are designing new representation. Posit is one example. Like there's bfloat 16, the TensorFloat 32 was just proposed. Like it's a 19-bit representation, like it's a couple of years ago. And then there is Microsoft has this MSFP, which is a block floating point representation. Then there is FlexPoint from Intel. Like everyone is designing new representation. So it's a great time to be thinking about numerics because performance matters, right? So our goal is, can we design a single polynomial approximation that produces correctly rounded results for multiple representations and multiple rounding modes? And this research, we have been working on the RLIBM project for like 2 years. And one night, like John sends me a note, oh, I want to mandate correct rounding for posits. Can you have a single polynomial approximation that works for like multiple? Like let's make like posit 32.2 to 8.2 the common way to change the precision of the posit representation. That got me thinking, and then we started looking at like why is it hard to produce a single elementary function, single implementation that works for multiple representations? So we all know like there's a 64-bit libraries out there, right? Like, and CRLIBM is a correctly rounded 64-bit math library. So why don't we just use it to produce correctly rounded results for like bfloat 16, which is 16-bit representation, or a 32-bit float? So let's say we are looking at log 2 of x, which is an elementary function, and then we wanted to produce a result for a 32-bit float. We don't have a correctly rounded float library. We could take the 64-bit library that is available from CRLIBM. You have your input in the floating point representation. You convert this into double. Okay, And then you call the CRLIBM or any of the available libraries. You get the output of the library in double, and you round it back to float. So unfortunately, it turns out that you don't get correct results for all inputs. Yeah, it may be close enough if your library has reasonable amount of precision, but it will have wrong results. And this is due to double rounding. Okay, this is the double rounding error. So what is double rounding? So at the bottom of the slide, I'm showing you the representable points with a double representation. Again, like this is not according to scale. Double has a lot more values compared to floating point. I can't plot all of them. This is for illustration purposes. So you have an elementary function. The star indicates the value of the elementary function in reals. Okay. So let's say we are looking at a correctly rounded library. The first rounding occurs when the double library rounds the real value into the double representation. Okay. So the first thing to note is this real value is less than the midpoint between the two floating point values you have in the second row. Okay. But when you did the rounding, first rounding, you lost this information. When the value is very close to the rounding boundary, you lost that information. When you round this double value back to float, you rounded it wrong. Rounded it to a wrong result. And what is the wrong result? Like if you had taken the original real value and directly rounded it to using the floating point representation, you would have rounded it to the blue dot. So this is the double rounding error. So we want to avoid, if you're going to design a generic library that works for lots of representation, you want to avoid double rounding error. Okay. So and what is our key insight? So when you do, to avoid double rounding errors or to avoid wrong results in the presence of double rounding, when you do double rounding, it has to maintain enough information about the original real value. So what is required for rounding? Typically, if you're doing let's say you're rounding with respect to two adjacent floating point values, you need three pieces of information. One, is the real value less than the midpoint of two adjacent values? Is it exactly equal to the midpoint? Or is it more than the midpoint? If you have these three pieces of information, along with the adjacent two floating point values, you can do correct rounding. So our key insight in the RLIBM project to make that allows us to design correctly rounded libraries for multiple representations is based on this observation that if you want to avoid double rounding error, preserve this information. Okay, so let me tell you like the high level sketch. So if you want to create a correctly rounded library for a representation with n bits or lower, okay, or with any rounding mode that is recommended by the standard, like let's say in this case IEEE 754, 5 rounding modes. So then create a correctly rounded math library for an n+2 bit representation with the round to odd mode. So this is a non-standard rounding mode, which I'm going to describe. So let me repeat the insight again. So if your goal is to generate a correctly rounded library for a representation with n bits or lower, with any of the 5 rounding modes, create a correctly rounded library for an n+2 bit representation with the round to odd mode. So what is this round to odd mode? The round to odd mode is not new, actually. Like we found instances of it in the seminal Goldberg paper from 1991, when to avoid double rounding. So Goldberg wanted to convert a decimal fraction into a binary fraction, and he wanted to avoid double rounding errors, and there's an indication of round to odd. And similarly, Sylvie Boldo and et al. Have like a couple of papers on how to do extended precision arithmetic while avoiding double rounding errors. Okay. So if people have already done it, why didn't anyone design a math library with round to odd? So this is because if you're doing mini-max approximation, it's extremely challenging to reason about error in the context of round to odd. There's a lot of numerical analysis work with round to nearest ties to even, but people have done like seminal progress on it. And since people have been focused on round to nearest rise to even, and they've been primarily focused on mini-max approximations. They did not discover this insight. So our observation was, how do you construct correctly rounded elementary functions for multiple representations using this insight? So if you want to, you can probably apply the same thing with Mini-Max, but it requires new numerical analysis technique, new error analysis techniques to make this feasible. In contrast, with RLIBM, we don't care about real values. We only care about the correctly rounded result. It doesn't matter whether it's round to nearest rise to even or it's round to odd. Once you give an oracle that produces the correctly rounded result, we will take that as our starting point and we quickly do it. So this is the key reason why we have been successful in generating a single polynomial approximation that works for multiple representations. Okay, so now let me tell you what is round to odd. So round to odd can be described in 2 sentences, right? If a real value is exactly representable in your representation, it rounds to that value. Okay, if a number is exactly representable in your representation, you just round to that. If the number is not exactly represented, you need to do rounding. It rounds to a value, rounds to an adjacent value whose bit pattern, when interpreted as an unsigned integer, is an odd number. Okay, so now you may be wondering, why does this round to odd work? Like that sounds like magic, right? So as I told you just a few minutes earlier, what are the 3 pieces of information that you need to do rounding? 1, is the real value less than the midpoint of 2 adjacent values? Is the real value more than the midpoint of adjacent values? Is the real value exactly at the midpoint? Okay, so now let's take a real value. We represent it with infinite precision. Okay, and you have your representation has n bits of precision. So now look at the n plus 1 bit. If the n plus 1 bit is a 0, then your real value is less than the midpoint. If the n plus bit is a 1, and all the remaining bits from the n plus 2 bit are zeros, then it is exactly at the midpoint. If the n plus bit is a 1, or if any of the bits from the n plus 2 bit is a 1, it's above the midpoint. So now we capture the n plus bit. This is also called as the rounding bit for people who design floating point hardware. And the OR, a bitwise OR of all the bits starting from the n plus 2 bit onwards is the sticky bit. So typically, to do rounding, to round a real value appropriately, you need the rounding bit, you need the sticky bit, and you need the truncated value. If you have these 3 pieces of information, you can correctly round any real value to an appropriate representation. The round to odd mode exactly preserves this information. This is why you have n plus 2 bits, and the round to mode exactly preserves the same sticky bit and the same rounding bit, and the truncated value is unchanged. And this is why this works. Okay, so now let me go over the illustration that I had, like when you took a double value and you rounded initially the real value into doubles and then to floating point, how it flipped. So in contrast, like when you do the rounding with the round to odd, you will round to an odd value. So you're preserving the information that it is still less than the midpoint. And when you round this back, it rounds to the correct value. Okay, so double rounding is inevitable because you're designing a representative. You're rounding once from real to some finite precision representation. And then you're rounding it back to a lot of target representation. So you are going to do double rounding, irrespective of whether you want it or not. But what round to odd ensures you is, even when you're double rounding, you're not losing information about the original real value. And that was like our insight. So I'm giving you a high-level sketch of what the insights are. The mathematical proofs to show it works for every rounding mode is a bit involved, like our papers provide you all those proofs. Okay, so now what our proofs show is this will produce correctly rounded results for multiple representations. Okay, we have shown it, and there are some caveats which I'm going to display. So now, what is our algorithm to generate correctly rounded results for multiple representations? It's similar to the original thing. So for each float input, we are going to compute the correctly rounded result, but now with the round to odd mode. Okay, say the elementary function in question is log2 of x, and we want to do it, we want to produce correctly rounded results for multiple representations starting from 32 bits to 10 bits. And we compute the correctly rounded result of log2 of x in a 34-bit FP representation. Okay. And now we compute the rounding interval, which is the say interval of real values, such that every real value rounds to this correctly rounded round to odd result with a 34-bit FP representation. So it's the same thing as we had before. The only thing is now the rounding mode that we are using to generate the correctly rounded library with a 34-bit representation is round to odd. So the one thing you will notice with round to odd, if the elementary function produces an output that is exactly representable in the n+2-bit representation, in this case 34-bit representation, and its bit pattern is even, then the rounding interval is a singleton. Okay, so now doing polynomial approximation with singletons can be extremely challenging. Okay, so why? Because like the polynomial does not have a lot of freedom. So what do? So what is a floating point output, or what is a floating point number? It is a rational number, and you have a transcendental function which is producing a rational output. We want to filter them so that like our polynomial in approximation has a lot of freedom for the remaining inputs. So this problem of identifying rational output, identifying rational inputs of elementary functions that produce rational outputs is well studied by Weierstrass and many others. So we use the results to identify all inputs for which the output of the elementary function is a rational value, and its bit pattern is even. Okay, so in the context of log2 of x, when do you get a even result? When do you get a rational result? Whenever the input x is 2 to the power of 5, and I is an integer, I is an even integer, I is an even number. So because we want like log2 of x, the result is exactly representable in the representation and should be, the most bit pattern should be even. So we can identify this initially by catching them, and then we can produce the correct results using bit vector operation. Like computing 2 powers is very easy, so you just use some shifts and you produce the result. And what you are remaining with, what you are left with, is the set of rounding intervals for the round to odd. Now use the exact same LP formulation that we had, generate the polynomial, and this polynomial produces correct results for all representations starting from n bit to e number of bits, where e is the exponent of the representation that we are looking at. Okay, so what are the 3 things I want to take away from this? Now, first, if your goal is to produce fast and correct math libraries, and you have an oracle, so then approximate the correctly rounded result. Okay, and once you decide to approximate the correctly rounded result, there is an interval around this correctly rounded result. That is your freedom. Now we use an LP. We frame this problem of generating polynomials as a LP problem, a linear programming problem, and we use state-of-the-art linear programming solvers, and there are like amazing results by others to solve linear programs of small dimensions. We use them and generate polynomials. There may be other ways to solve it too. So yeah, and what the bottom line is, this freedom by that you have by obtaining correctly rounded result is much more than whatever you get from a mini-max polynomial. And now, if you want to generate a polynomial approximation that works for multiple representations, and your the biggest representation that you're looking at has n bits, create a correctly rounded library for n+2 bits with the round to odd mode. And if you use the RLIBM approach, like approximating the correctly rounded result, it's straightforward out of the box. One thing you need to pay attention to is the issue of singletons, and that you can consult any approximation theory book. You have fantastic results, and you can do this. So what we show, both mathematically and empirically, is this produces correctly rounded results for numerous representations. Please see our paper or talk to me by email, or during the Q&A for the details about the proof. Okay, so does it work? All this is like nice fiction, right? At the end of the day, like what developers care about, give me a library that is fast and is also correct. So what we have done is we have generated a set of 10 elementary functions that produce correctly rounded results for all inputs, such that your representation has at least 8 exponent bits, and for any fraction number of any fraction bits ranging from 1 to 23 bits. So there are 23 bits. You have freedom. You can choose 1 fraction bit and 8 exponent bits, 2 fraction bits and 8 exponent bits, or 1 exponent bit and 3. You can experiment with it. So there are 161 such configurations, which also includes a bfloat 16, tensorfloat. All those come under this permutations with the exponent and the mantissa that you can play with. And there are 5 rounding modes in the IEEE standard. Like when you multiply them, there are 805 different configurations. A single polynomial approximation that produces correctly results for 805 different rounding modes for all inputs. So this was like fantastic. Like we were like really excited, and we pushed this. Now, like this is not just like a prototype code that we maintain on GitHub, right? With assistance from LLVM developers, now LLVM's libc uses correctly rounded functions generated by our approach, and it produces correctly rounded results for all 5 rounding modes in the IEEE standard. So again, not everything. Right now we have pushed 3 functions: lan of x, log2 of x, and log10 of x. Okay, so now this is fantastic. Like you have correctly rounded results. Is it fast? Okay, and how does it compare to other libraries? Like first of all, let's look at our competition, right? Take Intel's glibc or Intel's libc. Take glibc's libm, and even look at CRLibm. So all these produce wrong results for either some rounding mode or some representation. So the point to note is like CRLibm is a correctly rounded library. So a lot of people have invested a lot of time in developing them. So for doubles, for round to nearest, they produce correctly rounded results for all inputs. And they have different polynomial approximations for different rounding modes, like 4 distinct polynomial approximations for 4 different rounding modes. So when you just take them and round it, you still produce wrong results. This is due to double rounding. So in contrast, like if you're all you care about is 32-bit floats and the precision lower than 32-bit floats, you can use RLIBM and its functions. It provides you correctly rounded libraries. The next question that you may ask is, how much are you paying for this correct rounding? Is it fast? Okay. So in this slide, I'm showing the speed up of RLIBM functions compared to Intel's float functions and Intel's double functions. So since we are talking about speed ups, higher bars are better. Okay. So a line of 1.0 means our functions and Intel's functions are exactly the same. And we are using performance counters to actually measure the number of cycles. So if you look at like Intel's float functions, we are on average 30% faster than Intel's float functions. And Intel's float functions does vectorization, does a lot of sophisticated things to get this performance. Okay, and moreover, it produces like more than 100 million wrong results with about 1 to 2 alpha. So in contrast, we are faster and we are correct. We are correctly rounded. Our error is less than 0.5 alpha. And when we compare to double, Intel's double functions are a bit more accurate compared to its float functions. Compared to doubles, we are about 50% faster. And Intel's double functions are also produce wrong results due to double rounding errors. Okay, so in summary, we are faster than Intel's functions. And again, I don't want to take too much blame, right? I think this is the beauty of the idea here. So it's just 3 of us, like me, my student, and my collaborators working on it and building it. And Intel developers have invested years and years of work to generate this pretty good implementations. The fact that we can generate fast and correct libraries shows like the merit of the idea. So again, we are not solving table maker's dilemma. You're using the Oracle and generating fast implementations. Okay, so now you may be wondering, now if my goal is to look at correctly rounded, like how do you compare to CRLibm? CRLibm is a correctly rounded library for the double precision. Compared to CRLibm, we are almost 2x faster. So part of it is because like RLIBM is designed for double precision, so they need more accuracy, so they spend a lot of time optimizing it. So and RLIBM, when you repurpose it for flow, it produces wrong results. Okay, so hopefully by now I have convinced you it is feasible to generate fast and efficient, correctly rounded elementary functions. Okay, so even if you like slept through the entire talk, 3 things I want you to take away. One, if you don't want to tackle the hard problem of generating efficient oracles, so use an existing oracle and then approximate the correctly rounded result. Once you do that, you have a lot more freedom. You have an interval, frame it as an LP problem, you get really efficient polynomials. Then, if your goal is to have a generic library, one library that works for all, right? So then generate a correctly rounded library for n+2 bits with a round to odd mode. It produces correctly rounded results for n bits and lower. Okay, so I think it's high time we revisit correct rounding in the standards, at least for representations up to 32 bits. There is no reason why we should not be mandating correctly rounded results for at least representations up to 32 bits. So what does it take to do it for doubles? That's a research question. And as an academic researcher, I'm exploring it. When will we succeed? I don't know. So that's the luxury of being an academic, right? So all our prototypes and papers are available. And you can also see the conversation that we had in pushing these libraries mainstream with libc. Again, this is in collaboration with Paul Zimmerman from INRIA and Google developer Tu Lee and various others. Like, again, there is a nice community of researchers and practitioners who want correctly rounded libraries. And if you are interested in contributing, please get in touch with us. And finally, I want to thank National Science Foundation for seeing value in this work and generously funding both me and my student to pursue this line of. And thanks again for your attention. And I hope I convinced you that correct rounding is both feasible and can be made very fast.